All enjoyed shiny California this morning. So our first speaker of today is Professor Onur Mutlu from ETH Zurich. Unfortunately, he couldn't come in person due to a medical reason, so he will be remotely. And hopefully next time he will also not only give a lecture, but will also dance after he will recover. So, Onur.
Okay. Thank you very much, Shahar, for the nice introduction. I apologize for not being able to make it due to this emergency. I cannot walk on my 2 feet completely, but it's getting better. Hopefully we can have a nice interaction still. So I'm going to talk about memory-centric computing, which is a paradigm for doing computation near and inside memory. And I'll start with a summary slide, which I think summarizes most of the talk. So if you're sleepy in the morning, maybe you can digest the slide and go to sleep after that. So basically today, computing is a huge memory problem. Some people termed it an energy problem some number of years ago. And even that energy problem was due to memory. And I think this problem is going to increase and increase. So we have an energy problem, yes, but more importantly, we have a memory problem that causes the energy problem, or most of the energy problem. And memory is really responsible for most of the waste we have today in terms of energy, performance, robustness, monetary cost, and hardware real estate, and many other things. The problem is becoming worse with more data-intensive workloads, as we readily witness in AI and other domains. And I believe we can actually solve it by changing the paradigm, which is not going to be easy, but we will need to do a much more memory-centric design and architecture and system design. And in this talk, I'm going to look at 2 aspects of it. We're having a lot of difficulties with technology scaling, both in terms of compute, but more importantly, in terms of memory, especially DRAM. And if we can actually take a much more memory-centric view of memory, we can solve these issues much more easily. So far, we've been very processor-centric in the management of memory. If we can enable memory to be autonomously managing itself as an independent agent, we can do much better in the scaling. And then we're having huge difficulties in performance and energy of application and system scaling. AI is an example of this. Even though people are trying to scale the current learning models, it comes at a huge cost, essentially. And one of the major reasons, in my opinion, is really memory. And I'll give you some more data related to it. If we can enable memory to perform computation, meaning if we're much more memory-centric in our design, we can do much better in this. And the rest of the talk, I'm first going to motivate the problem, but then we're going to talk about these 2 directions to solve the application as well as technology scaling issues. And feel free to ask questions anytime. I think you can shout and I can hear. I'd be happy to stop. I have a lot of slides. I don't need to cover all of them. Some of them I'm going to rush through. Some of them I'm not going to spend a lot of time. Some of them I'm going to spend a lot of time on. So computing today is bottlenecked by data. Essentially, data is dominating how we do computing. And it's really key for many workloads. These workloads, AI, ML, genomics, databases, they all require rapid and efficient processing of large amounts of data. And data is really increasing. We can generate much more data than we can process in many domains. We have great data generators, not very good data analyzers. And we also want to perform more sophisticated analyses on more data. I'm going to give you a couple of examples very quickly. Probably you've seen this graph many times in the recent years. But essentially, with the growth of neural networks, these learning models, we need exponentially increasing compute power and exponentially increasing memory capacity and bandwidth. And to provide this, we need to look at new models. Otherwise, existing systems are not scaling. And I borrowed this slide from Cerebras Systems, where they're designing wafer-scale chips, which is an attempt to put a lot of compute and a lot of memory together. I think it's a good attempt. People should be doing that sort of thing. But I don't think it's going to be a solution completely, because the kind of memory you can put together with the kind of compute is not going to be very dense in that sort of technology. So we need to be looking at much more integrated technologies, in my opinion. Genomics is another domain where we do a lot of work on. We will work on algorithms and architectures for genome analysis. And here, data is really exploding. We actually have very good data generators. These devices, nanopore devices, for example, they're $1,000. So you can actually do genome sequencing at very low cost. Unfortunately, analysis is expensive. You need to move the data at the macro scale somewhere else to do the analysis. And depending on the sophistication of the analyses, you're really bottlenecked by the analysis. I can give you more examples. but we'll leave it for the later part of the talk. Essentially, we have a major performance energy bottleneck today, which is data access. And the way we treat data access, we cause great energy waste. Compute and memory are far away from each other. Data is sensed and then stored again in memory, and then stored again in caches, and then stored again in registers. And then eventually it gets processed. And then when you write back, you go through the same path again. So basically, we're moving a lot of data at both the macro scale as well as the micro scale. We're wasting a lot of energy. And also, we're wasting a lot of performance because moving data is not cheap. It takes latency and bandwidth. It takes time, basically. And we realize it's much more than we realize the energy waste. We actually complicate our systems to tolerate the data movement overheads. We add many levels of out-of-order execution, many levels of multi-threading, many levels of caching and prefetching into our systems in both hardware and software. And these methods that we employ complicate our systems, so it's not necessarily good for sustainability. They also do not work in many cases. So if you look at the caching effectiveness, more than 90% of the data and many large caches are dead, essentially. Essentially, even though these techniques sometimes work, most of the time they don't work, so they exacerbate the energy waste as well. So we're in this vicious cycle where we're wasting a lot of energy because we're moving data, but we're also wasting a lot of energy because we're trying to tolerate the latency aspects of moving data, and those mechanisms are not working very well. Okay, the main problem is we're very processor-centric in how we design our systems. All data has to go through some sort of computation unit. I call that the processor, and this comes at great system cost. Let's take a look at a couple of examples of the system cost. This is my cartoonish picture. When I was at CMU, I drew this picture in my NSF career proposal that I wrote to NSF. And we were at the time looking at quality of service aware memory systems, looking at how to enable predictable performance when you have many heterogeneous agents. So this picture is still somewhat the same. We have many cores or heterogeneous agents, the way I'd like to think about it. But that's not most of our hardware real estate. If you look at most of the hardware real estate of a chip or a single node today, it's really data storage and movement units. Caches, interconnects, other caches, memory controllers, other interconnects, main memory, other interconnects, storage. So most of our hardware resources is really dedicated to storing and moving data. In this talk, I'd like to take a blank slate approach. So if we were to design a system from the blank slate, how would we do it? And blank slate is good to think about from the perspective of a 10-year-old kid. If you have a 10-year-old kid, let's say you give this picture to a 10-year-old kid and say, I'm dedicating almost all of my resources, 95% of my hardware real estate or more, to storing and moving data. This should not be my bottleneck, right? They would probably say, no, this should not be your bottleneck because you're doing everything for it. Unfortunately, our bottleneck is still memory. So that was hardware real estate. Let's take a look at performance. There are many, many results. I'm going to pick one. This is a result that was published by Google in a beautiful paper that they wrote in 2015 for ISCA, where they analyzed all of their data center workloads on the state-of-the-art Intel processor at the time. And they essentially found out that most of the time, the processor is waiting for data to come back from memory. The processor is doing what it's supposed to be doing only 10 to 20% of the time, meaning finishing instructions. Again, let's take the perspective of a 10-year-old kid. Ask them the question, I'm designing the system. The only goal of the system for performance is to finish instructions. It's doing what it's supposed to be doing only 10% of the time. They would tell you that this is a terrible system. Go design something else. So we're going to be 10-year-old kids in the rest of the talk. Okay, that was performance. Energy is much worse. This is data that I borrowed from Bill Daly. Again, there are many, many results. I'm going to give you more results in terms of energy and performance later. But these numbers have changed, but what has remained is the relatives. So if you look at an arithmetic operation, a complicated floating point operation at the time, it's 20 picojoules. If you look at a DRAM access, that's 16 nanojoules. That's 800x difference. Okay, with better techniques today, better scaling, etc., you can get to 150, 160x, maybe. Essentially, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. Then the question is, do we really want to move the data to a computation unit on chip to perform computation? Of course, this is not dogma. This is really optimization problem. And the question is really, when do we want to move the data on chip? And for that question to answer positively, meaning to amortize the cost of energy that we expend to access memory versus to compute, we really need to have a lot of computation done on the same piece of data, meaning a lot of locality. And in many workloads, we don't have that much reuse, hundreds or thousands of reuse or locality essentially. And that was a complicated arithmetic operation. Today, we don't want complicated arithmetic operations in AI especially. We want simpler operations. We want one-bit operations ideally, right? But if you look at a 32-bit add operation, integer, again, similar results reported by this ISCA paper that was written by Bill Daly's group. The disparity between a memory access and that operation is 6400x. Now, if you actually reduce it to 4 bits, 2 bits, 1 bit, you reduce computation energy much more than you reduce memory access energy. And we're not even talking about storage yet. This is main memory. If you actually go to storage, multiply that by another 10x or so. So that number goes a bit crazy, like 64,000x. It becomes very difficult to amortize the cost of data movement to the compute units. Okay, we try to really understand the system level impact, end-to-end performance and energy impact of data movement. And we did a lot of studies to this end. I'm going to mention 2 studies that we did with Google. This is in 2018, we published. And we looked at the workloads at the time that is used on mobile systems by average users. If you look at the average use cases for TensorFlow inference, for example, Chrome browsing, video encoding and decoding, we found out that more than 60% of the total system energy in these mobile devices is spent on data movement. And these applications are memory resident, so we don't even go to storage in these. And this is average. Worst cases are much worse. And then we repeated the study with Google on machine learning accelerators that are used by Google, edge TPU essentially, on edge neural network models that are proprietary at Google. This is before LLMs. These were actually transducers, LSTMs, TNNs, RNNs, etc. And we found out that more than 90% of the total system energy is spent on memory in large machine learning models. One of the reasons is once you accelerate computation, memory becomes a bigger bottleneck. And the other reason is, of course, these are quite memory-intensive applications. I'm going to talk about this paper maybe a little bit more when we get to time. But if you look at the large machine learning models at the time, LSTMs, transducers, most of the energy is spent on DRAM and off-chip interconnects. Okay, so basically, processing of data, we have a fundamental problem. We're processing data far away from the data, so we're moving data a lot, and this is not good for many metrics that we care about. To fundamentally solve this problem, we really need to change the paradigm. We can, of course, do a lot of patches to the existing system, but in the end, we're not going to get rid of the fundamental cause of the data movement. If you want to really minimize the data movement, we need to process data where the data resides or where the data is generated. So we need a much more data-centric paradigm of computing. And there are many places where we can process data. This is something that could be in your pocket. And we're restricting the processing of data to a very small fraction of the system today. This SRAM-dominated chiplet, a very small fraction of it. Not even the SRAM inside this chiplet is capable of computation, but we want it everywhere. Inside DRAM, inside storage, inside sensors, anywhere basically. Okay, this is easier said than done. And there are multiple models of thinking about it. I think the simpler model that I'm going to take in the rest of this talk is using memory as an accelerator. Basically, we would like to offload functions, instructions, applications to memory. And we're very used to the accelerator model. We have a lot of compute-centric accelerators on the other side of the memory bus. Why not have some accelerator the memory side of the bus, essentially? There's actually an even better model going into the future, in my opinion, which is not having a central processing unit. Accelerator kind of implies that there's a central unit that's more dominant. If you have distributed agents that are actually processing data independently and they're communicating and they're all equals, that's in my opinion, much more fundamentally data-centric, but I think that's going to be harder to achieve given the current affairs. So we're going to take the accelerator model. Even in this model, it's not easy, essentially. Basically, we would like to put computation to the memory side. And the rest of the talk, I'm going to focus especially on main memory. I'm going to mention storage a little bit, but main memory is going to be our main focus because it has huge amounts of data today. And we're going to offload computation. Essentially, some compute engine is going to query it, ask questions, can you execute this function for me? And the memory is going to say yes and return the results, assuming it's capable. There are many questions here, of course, some of which we're going to tackle in this talk, and a lot of it is actually still subject to research. How do we design the compute-capable memory and the controllers? How do we design the processors and the communication units to enable this? How do we rethink the processors after computation is enabled on the memory side or some other parts of the system? How do we design software and hardware interfaces to take advantage of this computation capability? How do you design the system software compilers and languages to actually make it easy and actually get the highest performance and efficiency out of this? And how do we map our algorithms to the underlying hardware substrates, which may be actually very different, and we will see different models today. And I think my favorite is really theoretical foundations of computation. If you think about the theoretical foundations of computing, when we quantify the complexity of algorithms today, we really count operations. We're very processor-centric in how we think about computing theory. But maybe that doesn't matter as much based on all the results that I've given you so far. Maybe we should be actually developing a data-centric theory that's much more focused on data movement, that's at the center, as opposed to counting operations. So it's quite exciting, but it's also challenging. Essentially, it's an across the stack problem spanning devices and algorithms and everything in between and theory. I should also say that we're not the first ones to think about it. Clearly, there are many smart people who walk this earth. I'm going to mention two. If you know actually earlier papers on this topic, I'd be happy to actually change my presentation and papers, etc. But these two papers are the clearest examples of processing near memory. They called it logic in memory at the time, Potts and Harold Stone. They have papers from 1960s. And many people have examined this idea over the course of many years. Maybe the conditions weren't right. So you may ask the question, why should we look at this today? Basically, in my opinion, we have nowhere to escape. Today, we're at a point in technology scaling. I'm going to pick the first one at the bottom over here first. Technology scaling is not going well. And we're having a lot of issues in technology scaling of DRAM, flash, and these technology scaling issues demand intelligence and memory. We're also exploring emerging technologies. These can enable new functions in memory. I'm going to talk about this first. This is the bottom device level or circuit level perspective to actually push computation near memory so that we can actually fix the issues that are happening inside memory. The higher level perspective is application and systems are also not scaling very well today. I already given you a lot of data on this topic so far: data access, energy and power, and data moment energy dominating computation energy. And we have never been as constrained by these metrics as today. And today we're also at a very different point: performance, energy, and sustainability. We want all of them at the same time. There used to be a point where performance was dominant constraint. At some point, energy was important, but not as important as performance. Today, energy is as important as performance. We don't want to trade off between performance and energy. We want to improve both performance and energy, and also not hurt sustainability at the very least, but improve sustainability. And I believe we can actually improve all metrics by minimizing data movement. So we're kind of pushed in the middle. Designs are really squeezed in the middle of applications and systems and technology not scaling very well. Okay, let me jump into the first part of the talk, which is really the technology scaling aspects. And I'm going to advocate a memory-centric approach to technology scaling issues. And we're going to go into computation acceleration. So we have built a lot of infrastructure in my group for about 15 years or so to understand memory, especially DRAM, but also flash memory. I'm going to talk about DRAM in this talk. These are FPGA-based infrastructures where we built soft memory controllers, and we built a lot of hardware to actually modulate temperature, voltage, visual power, etc. So we can actually modulate a lot of parameters to understand what's going on in memory. This is our lab at ETH. We have two rooms, roomfuls of these devices where we can test a lot of different kinds of memories, including DDR4, DDR3, HBM, LPDDR. This was the infrastructure at CMU where we did a lot of the RowHammer experiments. And this is the original infrastructure, the bottom right over here, which was the makeshift infrastructure. So we open sourced a lot of these infrastructures so people can actually do a lot of testing. The more recent version is this DRAM Bender, of which there are multiple prototypes, and other people have been using it also in industry as well as academia to test the DRAM chips. And I believe it's important for us to understand the operational characteristics of these chips to understand their robustness, performance, and latency problems. I'm going to give you a lot of examples from this infrastructure. If people are interested in actually testing real chips and understanding what's going on and discovering new issues, we'd be happy to support as much as possible. This is all open source. You need to provide the FPGAs, of course. So one of the things we studied very heavily is the RowHammer problem. This problem is very well known by now. We started studying in 2012. We published this paper in 2014. Essentially, the problem is you can induce bit flips in memory locations in DRAM just by accessing DRAM without modifying anything, meaning without intending to modify anything. Essentially, you can cause silent data corruption with particular access patterns. I'm going to give you the basic idea. I'm not going to give you a lot of details of it. We have a lot of papers, and other people have a lot of papers on the topic. So if you have DRAM, you have two-dimensional array of memory cells, rows and columns. If you want to access one cell, you need to activate the row or apply high voltage to the word line belonging to that cell. This is called opening the row or activating the row in DRAM. Now, if you want to access another row, you apply low voltage to this row, meaning you deactivate the row or pre-charge the array. Now, if you keep doing this repeatedly, legally, many times, high voltage, low voltage, activate, pre-charge, open, close, open, close, open, close, enough times before the cells get refreshed, it turns out some physically adjacent cells that are vulnerable lose their charge little by little with every activation. And if you do it enough times, their charge can get depleted. So essentially, you lose the data that's stored in those cells. So this should not be happening clearly because we're just reading from memory. And we found out that essentially all DRAM chips that you can buy are vulnerable to this problem. In 2012, it was most DRAM chips, but today it's all DRAM chips. And there are very interesting circuit level reasons, device level reasons. I'm not going to go into it, but essentially the key takeaway is there's some crosstalk or coupling that's happening between the two rows that if you activate one row, you're causing disturbance in adjacent rows. And this can be induced by a user level program without any privilege in the system. And this becomes much worse with technology scaling. Essentially, the reason this happens is cells are too close to each other and cells are too small. If you make the cells even closer and even smaller, which is what technology scaling is, this problem becomes worse. Over the course of 10 years, we've tested a lot of chips and we've looked at different mechanisms. And we found out that the vulnerability, meaning the number of activations to induce a bit flip, reduces by more than 10x, more than 100x in many cases. So even benign applications can induce these bit flips today if there were no RowHammer mitigations at the circuit inside the device. Okay, I will not bore you with a lot of details. We've written a lot of papers on this topic. This is the original paper. There's a lot of work in many communities, but especially the security community took these bit flips and they exploited them at the user level to take over a system, read data they do not have access to, break out of virtual machine sandboxes, corrupt important data like render ML machine learning inference useless by reducing its accuracy, and steal secret data like cryptographic keys or machine learning model parameters. In fact, if you're following security, this year's Usenix security was held about 2 weeks ago, maybe 3 weeks ago, and there were 7 papers on RowHammer still after like 12 years of within 12 years of publication that showed different attacks. One of the attacks was very interesting. They actually were able to induce these bit flips on GPUs, and they were able to essentially cause ML inference on GPUs to become very low accuracy. Okay, there are many papers. So the reason I'm telling you all of these is because these kind of scaling issues are going to get worse. More recently, about 2 years ago, we discovered another read disturbance mechanism. We called it row press. This is fundamentally different from RowHammer, even though it's related. It's another read disturbance mechanism. And the idea with the row press is, with the RowHammer, in order to cause disturbance at the maximum level, you activate a row, you keep it open at the minimal amount provided by the standard, and you keep activating, closing, activate, close, activate, close, activate, close, at the maximum possible rate that's allowed by the standard. Now, with row press, we found out that if you activate the row and keep it open at the maximal rate, or more than what is the minimum amount allowed by the standard, you actually induce even more disturbance due to different device level mechanisms. And this way, you can actually induce the first bit flip with much fewer activations, 1 to 2 orders of magnitude, smaller number of activations compared to RowHammer. This is fascinating because it affects all the DRAM chips essentially. And all DRAM manufacturers, Samsung, Hynix, Micron, are vulnerable to this. And in extreme cases, with only one single activation, you can use this bit flip. So we're reaching the scaling limits of technology, DRAM technology here, at least in the current fabrication methods. Okay, so this means that you need to find solutions to this problem. When we actually wrote the paper, there were no device level explanations of this or documentation of this. Later, folks read our paper and they actually developed device level models to really explain why this is happening. So this is also fascinating to me. Normally what happens is people develop some theory at the device level and then they build systems on top of it. In this case, we're actually discovering things at the system level, but device level explanations are coming later. So I kind of like this interesting state of affair where we are in DRAM technology scaling today. Okay, so I can give you more examples. I'm going to give you a couple more. But the solution, how do we solve this problem? If this were a RowHammer talk, I'll give you many, many solutions, but I'll give you the gist of it. Essentially, we need intelligent controllers. It's very easy to solve this problem at the device level, circuit level, forget about the software level. You really need some hardware controllers that understands the device properties and adapts to it. And we've argued for this for many years. This was a paper that we were invited to write 12 years ago at the International Memory Workshop. And we argued a very similar thing. We wanted system memory co-design and intelligent controllers. 12 years later, we were invited to a similar paper at IMW. And I think at this point, memory has become a much worse problem over more than a decade. And we wrote a similar paper. Now, the good news is industry, even though they were quite skeptical initially about this, finally they're, I think, following a good direction. The specific solutions may need work, but the direction is a little bit more memory-centric than what was thought of before. This is a paper from ISSCC 2023 by SK Hynix, one of the major DRAM manufacturers. This is the first paper that essentially publicly acknowledges RowHammer by a DRAM manufacturer. They basically say they built an intelligent memory controller inside the DRAM chip to solve this problem. I'll give you the basic idea. Essentially, with every row, they add an activation counter. And inside the DRAM chip, this activation counter gets incremented with every activation. And if the number of activations to a row is greater than some threshold, the DRAM chip takes a mitigating action, which is probably refreshing some adjacent rows so that they don't get disturbed, let's say, disturbed too much. So this is an intelligent controller inside the DRAM chip, actually. You could argue whether it's a good solution, bad solution. I'll leave that to some other discussion. We have papers related to that also. But this is a more memory-centric solution. Essentially, it enables the memory to somewhat manage itself, although it's still restricted to the unfortunate DRAM interface, which is controlled by the processor memory controller. So there's some artifacts where the processor needs to initiate a lot of these actions. So the memory controller, the memory itself, the DRAM chip itself, is still not completely independent. This was standardized by JEDEC 1 year later in 2024. This is actually based on a lot of the work that we have done and others have done. So in the end, JEDEC standardized the solution. So it's going to be in all of the DRAM chips going forward. The question, of course, is, are solutions good? And this is one solution to disabling access to the other side of the walk path. And if you ask the 10-year-old kid or 50-year-old kid or 80-year-old kid, they would all tell you that this is a terrible solution. Right? It's good to ask this question always. We write papers about it, and we have better solutions to this. Again, all of those are memory-centric, meaning you need some intelligence on the memory side to solve this problem. So I'm going to give you one example of an even better memory-centric solution, which is self-managing DRAM. This is the work that we published last year. And the idea here is, today, DRAM is essentially a slave, or memory is a slave for the processor. It has no say. It cannot initiate any independent operation. It cannot even refresh itself unless the processor chip tells it to do so. We would like this to change because this is not good for example, RowHammer management, refresh management. We can have much better, much more efficient management mechanisms implemented inside the DRAM chip that can understand which rows need to be refreshed how often. And we can implement these without changing the DRAM interface and without changing the memory controller if we actually had given the DRAM chip some freedom. And the idea is very simple. Give the DRAM chip a little bit of freedom, a little bit of breathing room by changing the interface just a little bit. Essentially, that interface change empowers the DRAM chip to be able to say no to the DRAM controller. If the memory controller sends an activate, the DRAM chip can say, oh, this activate is coming to a region where I'm doing some operations on. Memory controller, you cannot access it. I'm not going to obey you. So try again later. That's the idea. Memory controller still orchestrates access operations, but the DRAM chip orchestrates or performs maintenance operations by itself. And this is, I think, a nice interface that moves the completely processor-centric interface to become a little bit more memory-centric, not completely, a little bit more, giving the ability to say no. Okay, so we evaluated this for DRAM refresh, different types of DRAM refresh, like variable rate refresh, fixed rate refresh, different types of RowHammer protection, different types of memory scrubbing. This is also good for doing computation inside memory. And we found out that you can actually improve efficiency and performance. And more importantly, you can enable innovation on the memory side, because today innovations on the memory side is really limited by the changes you can make to the DRAM interface. And that DRAM interface is very, very difficult to change for everything that you want to do, because the standard, at least the standard interface requires vetting by hundreds of companies that are part of JEDEC, which is a very poor political process, in my opinion. It doesn't really consider technical arguments as much. Okay, so I believe there's more to come in this area. We need to really rethink the interface to memory such that we can enable better partitioning of processor work between the processor and memory systems. Let me give you a little bit more concern very quickly again. So what worries me even more is aging. And we have seen evidence based on our results that as DRAM chips age, they become much more vulnerable to bit flips, including RowHammer. And this is some data that we published. We are studying this effect more. Now, if you send these DRAM chips, cutting edge technology to space, and if you really want to keep it over there, that worries me quite a bit, because we don't know how these chips will behave in adverse conditions. We're trying, but it's difficult to get all of the data. This is one of the works. And more recently, we keep discovering new issues with DRAM. This is one thing that we discovered this year in 2025. And we found out essentially that the read disturbance threshold, the number of activations to induce a bit flip over a row, changes randomly and unpredictably over time. This is what I call quantum-like effects in highly scaled circuitry, which means that accurately identifying the RowHammer vulnerability, or when you should really take an action, when you count the number of activations, is challenging. So you keep testing and testing and testing for days and days and days, months and months and months, and you discover worse vulnerability over time. We call this the variable read disturbance phenomenon. And again, there is no device level explanation of this phenomenon that we could find. So hopefully a device level theory will be developed. But this sort of thing cannot be handled offline, meaning you need to have actually even more intelligent memory controllers that understand how different operational properties of DRAM change, and they need to adapt over time by profiling DRAM. So we actually need even more intelligence on the memory side. You cannot configure these solutions with static thresholds, because those thresholds change over time by aging with quantum-like effects like variable read disturbance. Okay, you may say that DRAM is old technology. That's true, but that's also a new technology in the sense that it's evolving into the future. We have 3D DRAM, VCT DRAM, etc., that's being investigated. They all have robustness issues at this point, but at some point we're going to scale more. But all of these technologies will have similar issues. And emerging memory technologies, in my opinion, are not a solution to this problem. I actually enjoy working on emerging memory technologies. We've been working on them for a number of years. This is one of the papers that we wrote 15 years ago on phase change memory. Unfortunately, emerging memory technologies either immediately require an intelligent controller or memory-centric perspective off the bat, because they have very difficult issues like endurance, like wear out, or we have not understood them well enough because we have not scaled to the dimensions that we have scaled DRAM and flash into. And if you look at DRAM and flash, we've scaled them to very small dimensions. And as a result, we need these intelligent controllers. I didn't talk about flash, but for flash memory, you need intelligent controllers off the bat because of the wear out problem, plus the scaling issues. So I believe we have nowhere to escape. On the memory side, we need to be much more memory-centric, enable memory to manage itself. Now, that's why we're actually building a lot of infrastructure to understand memory more. We'd be happy to get help. We'd be happy to help other people if they want to develop this sort of infrastructure as well. Now, the good news is there's actually a lot more acceptance from the community compared to 12, 14 years ago. Today, we see a lot of read disturbance sessions at HPCA, ASPLOS, ISCA, many major architecture conferences and other conferences. And also, I mentioned the security conferences. And we recently held a DRAM security workshop with ISCA. And there was a nice panel discussion. You can find all of this on YouTube, actually. The panel discussion was held between a lot of industrial folks who are discussing solutions to RowHammer. It's a nice, interesting discussion if people are interested in this topic and how industry views this problem. Okay, this is the point. I'm going to switch some gears, but if people have questions, I'd be happy to take them now. I know it may be too early over there.
Do we need a question?
Yes, otherwise
hold on, Cliff, hold on.
There's a question coming.
Can you hear me?
Okay.
Yep. All right.
Yes, I can hear you.
Hi. So what's like a standard solution to? I mean, this happens. Is it easily detected? Do you use error correcting codes? Like, what's the standard solution to this problem?
Yeah. Okay. So the currently standardized solution is what I described in JEDEC. Essentially, each DRAM chip will have a counter added next to each DRAM row. And these counters will be incremented whenever you activate. And the DRAM chip will take some action to mitigate the read disturbance, meaning potentially refreshing adjacent rows if the counters are greater than some threshold. That's the standard right now. It's not described in more detail than this. It's a framework of solutions. And DRAM manufacturers have, let's say, some freedom to implement things a little bit different. You mentioned error correction codes. They could help the problem, but we have done a lot of studies on this topic, as well as a lot of others. You get a lot of bit flips. So if you really want to prevent these bit flips you need to have very strong error correction codes. The overhead of those error correction codes are much higher than the overhead of the activation counters.
So do the chips?
But of course, you can combine multiple solutions as well.
So do they just throw the chips out when the counts get too high? Or?
No, so this is an online solution. This is an online activation counting solution. When you're actually accessing the chip, these counts get incremented. When the counts get too high, you refresh the adjacent rows. You can also offline them for some time if you want. But essentially, it's an online solution.
Any other questions? Yep. Should we identify who you are to the speaker?
Hi, this is Mark Horowitz. I'm going to prefetch something because you're talking about how the fact that the noise margins in the DRAMs are actually not that good, right? That's what's causing the bit flips and other kinds of problems. But then I think you're going to talk about using memory. You're going to make those margins even smaller. So I'm just prefetching for you because I'm really curious what your take is on that. Does it make sense?
Yeah, of course, yes. And we have a lot of analysis of the interactions of these things with our real experimental infrastructure. So we have examined a lot of these things. I'd be happy to share them. I'm not sure if I'll be able to share these in this talk, but for example, if you actually do processing using memory, using multiple row activation, that exacerbates the RowHammer problem. So we need to actually have solutions to these things. But we also have very promising examples where we actually see real functions in DRAM by activating multiple rows, even though the DRAM chips are not manufactured for this purpose. So I think there's upside and there's downside. It's a more challenging promise than actually processing near memory, which is actually designing logic. But it's good to examine it for the future. Okay. Did I continue, or is there another question?
I think we're good for the moment.
Okay. So I think I have not a lot of time, so I'm going to jump to processing using memory. I'm going to cover processing near memory very quickly, since maybe I'll try to take a vote remotely. But essentially, we're going to jump into accelerating applications in memory. And the terminology in this area is a bit terrible. Sorry. And I'd like to correct some of the terminology, I think. People called it logic in memory in the 1960s, and I like that terminology, but it's a bit tough to use the exact same terminology. I'm going to call everything processing in memory. But in terms of nature, I believe there are only two types of processing in memory. One is processing near memory, and the other is processing using memory. Processing near memory is very similar to what we do today. We design logic separately from memory. There's a logic process, there's a memory process, even fabrication technologies may be different. But we decide to put logic at some distance from memory. Processing near memory says put logic as close to memory as possible, basically, so that you can minimize the data movement and overheads. We could be putting the logic in the memory controller. We could be putting the logic inside the DRAM chip. We could be putting the logic near each subarray, near each bank, near each cell. Of course, there are overheads associated with it, or in the logic layer of 3D stacked memory. So that's business as usual in a sense, but we put logic near memory. Processing using memory is fundamentally different. We don't have logic. Forget about logic. We have memory. Any memory has some operational properties, analog operational properties, that enable it to do computation. And we're going to exploit those operational properties. And this is clearly going to depend on the memory technology, and the capabilities and the benefits will depend on the memory technology. I'm going to especially look at DRAM and flash, because we've done a lot of real chip studies with DRAM and flash. But this is true for other technologies, memristors, for example, RRAM. Some folks like Shahar has been focusing on very interesting designs like that. But I think in the end, we need to examine both. Processing near memory is easier because it's closer to the business models, even though it's far away from the business models, but it's closer. And you can have much more capable logic next to much denser memory. In processing using memory, you're going to be limited to what the memory technology is capable of, but you could be much more efficient compared to processing near memory. And you may need to map your algorithms much more carefully to the substrate. In the end, I think we need to combine both. Now, let me quickly go over processing near memory. I think I don't have a lot of time, so I'm going to skip a lot of these things. The good news is industry is examining this seriously. We worked a lot with the UpMem company, for example, which manufactured DRAM chips, DDR4, and they added essentially a processor next to each bank. This is a multi-threaded processor. Their model had a lot of limitations, et cetera, and we documented a lot of those limitations. But this was a prototype chip on top of which we could build software stacks. And we built a lot of actually software stack algorithmic mechanisms, as well as benchmarking tools, compilers, and data parallel programming frameworks, for example, on this UpMem system. So if you're interested in actually getting your hands on to a real system that has processing next to each DRAM bank, this is the system. They were recently bought by Qualcomm, but we'd be happy to try to get you access to it because we have a bunch of these in our lab. Samsung, SK Hynix, and Micron, they all have put, and Alibaba, they all have modified the DRAM chips to put essentially multiply and accumulate accelerators next to each bank. This is, again, processing near memory. Logic is designed separately from memory. And these are not publicly available to my knowledge. They have been publishing results related to it. So the good news is there's actually a lot happening in industry in this direction, and there may be a lot more to come. And I think with interfaces like CXL, Compute Express Link, there's a lot of opportunity to offload computation more, let's say, freely, essentially free the processor from doing computation. Okay, again, I'm going to skip some of these slides. We've done a lot of work in processing memory, but we don't have a lot of time, and I want to focus on processing using memory, which is more futuristic. We've accelerated graph processing, for example, near memory, and designed remote function call-based models where you can actually ship the functions to the data to process graphs. And we've shown significant benefits in graph processing. I'm going to skip these. And these are the papers. I'd be happy to share the slides on the website. We actually looked at full stack designs where we looked at graph pattern mining, where we designed set-centric instruction set architectures where set operations are ISA operations, set intersection, set union. And these set operations are actually very well supported by processing near memory, very simple logic, bitwise logic, which is going to be supported by what I'm going to describe in processing using memory. And we designed algorithms, graph algorithms, to actually map to these set abstractions. So that's a full stack design where algorithms are designed to actually match the hardware's bitwise set in union and set intersection capability. ISA is also designed to actually take advantage of it. We see even more significant benefits. I showed you big benefits earlier, like in this paper, more than 10x, more than 10x. You get even more significant benefits. You can actually change the stack. We've looked at accelerating machine learning inference with Google. I'll spend a little bit more time on this one. We actually analyzed a lot of neural network models with Google, and we found out there's a huge diversity in terms of the execution characteristics of these models. You can see that there are some layers from CNNs and RNNs that are extremely compute intensive, and there's some layers from LSTMs and transducers that are not compute intensive. The parameter footprint is huge, and the compute intensity is very low. And designing a single accelerator like the HTPU to cater for all of these layers is essentially not efficient at all. So we argued, there's more data on diversity. We argued for designing multiple different types of accelerators to cater to different types of compute and memory intensity requirements of machine learning layers. So in this particular case, we designed 3 accelerators because we found 3 families are dominant. One is very compute-centric accelerator, and 2 of these are memory-centric accelerators. This way we can offload layers using a runtime system to these different accelerators. It's essentially a heterogeneous edge TPU, if you think about it. Okay, and we see significant benefits in terms of both performance and energy, more than 3x improvement in terms of performance and 3x improvements in terms of energy. Again, I've summarized a lot of these, but there's a lot of evidence in the field that processing near memory works, and there are different levels of like end-to-end execution model for it. You may want to offload only functions, for example, like we did over here, like layers, or you may want to change the entire stack and rewrite your algorithms to actually take advantage of near memory processors. Okay, we've done more studies, but I'm not going to bore you with these. We've looked at a lot of genomics workloads. These are actually even better because in genomics, you have a lot of, you don't have sophisticated arithmetic operations. It's easier to do these operations. And in some cases, the data sets are so large that memory, doing these things in memory alone doesn't make sense. So we actually moved a lot into storage. This is a very recent work where you actually, metagenomics, essentially you take samples from the environment and you try to identify different kinds of species that are lurking over there so that you do analyses on it. And here you need to query databases of hundreds of terabytes, which you cannot really store cost efficiently in memory. So we develop a lot of in-storage processing methods for this. There are many more examples in this paper that we keep expanding. It's almost 100 pages, and it's very hard to keep up with the research in this area. But if you have any suggestions, we'd be happy to expand this more. More recently, we've looked at large language model inference and more recently training, but we reported results on inference. Again, I think the principles are very similar. These applications have heterogeneous requirements. Large language models, for example, have different requirements. Some fully connected layers are extremely compute intensive and they should be processed in a GPU or TPU. So we designed a heterogeneous system for this processing. We have some GPUs and TPUs. And then some parts of the fully connected layers are actually memory intensive, but they have significant computational power. So the processing near memory system, they actually benefit from processing near memory, but the processing near memory system that you don't have very good computational power. So we design a system like that. And some parts of the large language models actually very memory intensive, and it requires a lot of memory capacity, like the attention layers, for example, at least in these models. And for that, again, you want to do processing near memory, but it could be disaggregated a little bit farther from where you do the main processing. And your computational capability in the near memory processor side doesn't need to be that high. Again, this is very similar to a heterogeneous TPU work that I mentioned earlier. So I think some of the fundamental principles remain, but we need to actually design the systems such that we can identify what parts of a workload should be executed where, and what kind of configuration that we want to use in terms of compute-centric and memory-centric accelerators. I'm going to skip this one, but we also try to eliminate GPUs in some of the work to understand whether we can accelerate LLM inference without GPUs. And here, CXL and its communication mechanisms, and again, computation capability inside the CXL devices helps a lot. Okay, I covered processing near memory relatively quickly, but if there are questions, I'm happy to take them. I just want to give enough time to cover processing using memory because I believe this is the more challenging task, as Mark mentioned. But it's also something that we really want to explore, in my opinion, because it can actually revolutionize how we actually design algorithms and maybe how we actually build devices. Any questions on processing near memory or anything I mentioned before?
We lost your face. Can you turn your light on, or is that? I'm not sure exactly what.
Oh, okay. Just a second. Maybe it's a light issue. Yeah. It's a bit late over here. Sorry. Okay, lights. Try the lights over here.
But it's nice to see your face.
Okay, sorry. How about now? Better?
Yep.
Okay, good. Sorry. Yeah, it's almost 8 p.m. here in Istanbul. So. Okay, no questions? Okay, I'm going to go to processing using memory then. Okay, let's jump in. So this is a one-slide summary of what I'm going to talk about. Essentially, I'm going to focus on DRAM. Sorry. Is everything okay?
There's just one question. Hold on a second.
Okay. Okay, one question. Okay, I'll wait.
For processing near memory, when you have like the logic on the DRAM chip, it seems like mainly what you're cutting out is the HBM communication link to the main chip in terms of the energy cost. And so the question is, you said that the memory accesses had these huge expenses relative to computing. How much are you able to get rid of just by removing the communication link, and then how much of it is just fundamentally associated with accessing values from the memory itself?
Yeah, that's a great question. So most of the energy is really spent on the communication link in general. So if you eliminate the data moment on that communication link, you actually save a lot of energy, a lot of the energy. But then if you actually have a logic layer, for example, a true logic layer, a nice logic layer, like we envisioned some time ago, and you can communicate with the interconnects that's inside the logic layer, then it's local communication, right? You're not going through the large chip. So you can actually accomplish a lot inside the logic layer. And that's what we actually argue in many of our works, saying that inside the logic layer, you can be very efficient in communication, and you can connect many of the DRAM banks with that logic layer. Does that sound good?
Yep, we got a thumbs up.
Okay. Okay, great. Yeah, there's a lot more over here, but we went over it very quickly. Okay, I'm going to continue that until you interrupt me. So this is a one-slide summary of processing using DRAM works. As I said, DRAM is something that we've been working on, and we've discovered a lot of things. Initially, we built a lot of circuit theory, let's say. We based our studies on chart sharing. But more recently, we actually used our infrastructure that I showed you to demonstrate these functions. We can do a lot with DRAM, even without modifying DRAM and its interface. But I don't recommend it, let's say. I think we need to think about modifying DRAM and its interface to make these much more robust going into the future. But I'd like to demonstrate that we can do a lot even without doing much with the DRAM chips. So we can do bulk bitwise copying and initialization. We can do essentially all bulk bitwise operations, logical operations. We can generate true random numbers, physical and clonable functions. And if you want to do more complex things, we have developed methods for using lookup tables in DRAM. Most of these come at low cost. And the idea is to exploit the analog computational capability of DRAM, but don't stay in the analog domain for too long, because we have sense amplifiers in DRAM that immediately turn the analog value to digital. So we can actually amplify things quickly in DRAM. The main idea that I'm going to describe is activating multiple rows performs either computation or data movement. If you activate 2 rows consecutively, quickly, you perform data movement. You move one row to another. If you activate multiple rows concurrently, you perform some sort of computation. And I'm going to show you results with simulations, and I'm going to show you results with commodity off-the-shelf DRAM chips based on our infrastructure. And we see significant performance and energy improvements depending on the applications that you map and depending on the effort you spend to map those applications to the underlying substrate. I'm going to start with, let's say, cheating, meaning the simplest thing that you can do, data copy initialization. In my opinion, it's a no-brainer. Basically, data copy initialization is in many of our applications. Google, in the paper that I mentioned in 2015, did a lot of analyses, and they showed that only 2 function calls, memmove and memcopy, occupies 5% of their data center cycles. This is not all the data moment, just memmove and memcopy. And they said that we should be examining more approaches like what I'm going to describe next, because our paper was published earlier than their work. So how do we do data copy today? I'm going to look at bulk data copy, 4 kilobytes, 8 kilobytes, pages, let's say. But you can also do things with smaller data copies. If you copy this white page to this gray page, today you have to go through the processor. Byte by byte, everything goes to the CPU. If you know what you're doing, to the memory controller, to the DMA engine, but you have to traverse the memory bus. And you move the destination page byte by byte. Essentially, you move 12 kilobytes of data to copy a 4 kilobyte page to another 4 kilobyte page. Again, if you take the perspective of a 10-year-old, and if you give them this picture and tell them this white page and gray page are very close to each other in memory. They could be next to each other in the same subarray. They would probably tell you, why don't you just do this? And I think we should be at least enabling the ability to do that. I'm not saying we should always be doing this, but we don't have the ability to do that even in our systems. So maybe 10-year-old kids should be designing our systems because they don't have the baggage of business as usual. Okay, so this will be low latency, low bandwidth, no cache pollution, no unwanted data movement. I'm going to show you a mechanism that, in the best case, unoptimized, reduces the latency by more than 10x and reduces the energy, DRAM energy, by more than 70x. And the idea is very simple. It's actually doable in existing DRAM chips. Basically, this is the DRAM subarray. This is the row buffer, essentially the sense amplifiers. We first activate the source row, which brings data into the sense amplifier, strong in the sense amplifier, it's sensed. And then we activate the destination row in quick succession, which deactivates the source row and connects the sense amplifiers to the destination row. So by doing 2 consecutive activates with negligible hardware cost to make it reliable, we get significant performance and energy benefits. So we're basically exploiting the underlying operational structure and chart sharing properties of DRAM to do this back-to-back row activation, which leads to a copy. Now, I'm going to show you later results that if we abuse DRAM, meaning violate the activate to activate timing parameter when you're accessing 2 rows in the same subarray, this operation you can see in real DRAM chips, and it's almost perfectly reliable, like 100% we see in many cases. So even though the DRAM chip doesn't officially support this operation, by violating the timing parameter activate to activate, we see this operation to be almost perfectly reliable. I'm going to give you actually even a more sophisticated operation where we copy 1 row to 31 other rows. That's a little bit less reliable, but still almost perfectly reliable. So that's fascinating to me. Okay, so we call this row clone. What about computation? So I'm showing you here 3 DRAM cells, ABC. These are the capacitors. These are the access transistors. This is 1-bit line. This is the sense amplifier. This is the other end of the sense amplifier. And I'm showing you only 1 cell per row, but imagine you can do this operation on millions of cells in DRAM. Now, if you had the primitive to concurrently activate these 3 rows, A, B, C, in an ideal circuit, you would get a bitwise majority function. If at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. And that's bitwise majority. That's essentially computation. And if you set C to 1, you get the OR. And if you set C to 0, you get the AND. So basically, majority, OR, and AND relatively easily, let's say, easily in ideal circuits. Now, what is missing over here is NOT. You're not Boolean complete, but NOT is actually there. If you actually activate only one of these cells, C, let's say, you get the C bar on the other side of the sense amplifier. So you just need to supply it back to the subarray. And we actually have proposed multiple methods for doing so. Some of them are very cheap, well, relatively cheap. Some of them are very expensive. Doesn't matter. I think if you have a method for supplying this back to the subarray, then you can actually enable Boolean complete computation in the same subarray. Okay, so we actually did a lot of end-to-end system-level simulations using simulators. We mapped databases that are developed for maximizing bulk bitwise operations, like the bit weaving database, and we see significant performance energy improvements. And there are many other applications that can actually be mapped to it almost immediately off the bat. You just need to revise the application to the mapping to DRAM. And we mapped some of these. Again, I will not bore you with a lot of results. You can find a lot of results in our paper. This is a general purpose substrate, actually. You can actually accelerate any operation with this substrate, as long as you can rethink your algorithm in a bulk bitwise manner, and you can actually overcome the idiosyncrasies of what's happening in DRAM. We tried to make this more programmable. I'll go through a couple of these works relatively quickly. You can actually implement any operation with the substrate. Let's assume that you want convolution. You specify convolution or matrix multiplication using a circuit and or NOT logic. We converted to majority inverter graphs and optimize these majority inverter graphs using electronic design automation tools that are developed for superconducting logic, which actually operates on majority gates. We minimize those graphs, and then we create a microprogram associated with that instruction, let's say convolution. This microprogram does row clone, triple row activations, row allocation, etc. And we essentially have an instruction that can be executed using this microprogram. And then the compiler or the programmer inserts this into the program. And you are actually based on the sequential programming model. When the program actually gets to this block bitwise operation, it gets shipped to the memory controller, and the memory controller sequences through that microprogram to execute inside the DRAM. So we can actually do this, and we've actually done this on a real FPGA prototype, except our microprograms are just for row clone and true random number generation, because we can actually do those with real DRAM chips. I'm going to mention this a little bit later. So we actually have prototypes of this in real chips restricted to row clone and true random number generation. But if you actually do more in simulation, we see significant benefits. Okay, this is more on SimDRAM. So how can you actually take advantage of this even more? If you really want to take advantage of the even more, you need to modify DRAM even more. Meaning, you cannot do very coarse-grained processing in DRAM. Today, whenever you activate one row, you activate a lot of cells. But in many applications, the parallelism that you have, bit-level parallelism that you have, may not be 8 kilobytes or 4 kilobytes. So we actually want to target individual DRAM mats, like 512 bits or so, to be able to actually have fine-grained DRAM, meaning enable access to individual DRAM mats. So there are many people actually who have worked on this topic, including Mark over there, trying to have fine-grained access to DRAM for energy efficiency. We show that this is actually good for performance and also scalability for processing using memory as well. This way you can actually restrict some of the operations to some mats and do other operations belonging to other applications or the same application on the other mats. So you can actually exploit multiple instruction, multiple data parallelism in different mats in DRAM. And to take advantage of this, you need to have some sectoring in DRAM, and we have one proposal. That's a more recent proposal for fine-grained DRAM. Okay, so this is not enough, because for aggregation operations, for example, you still need some logic inside the DRAM chip. This is processing near memory. And we add low-cost interconnects. You can actually add more near memory processing if you want to be more powerful. And finally, we actually developed a compiler to target these mats. We modified the LLVM compiler such that it can target individual mats and can maximize the parallelism. And the good news over here is we don't need to target 8 kilobytes of data for parallelism. We can target 512 bits, which is the AVX vector width today. So again, I will not go into detail. This is all open source. Actually, almost everything I said is open source so far. The compiler that we use does auto vectorization, so very limited to some applications, but you can actually do this by hand also if you know what you're doing, let's say. And then we do code scheduling and data mapping on the DRAM arrays, and we do the code generation such that we can execute DRAM operations. If you do all of these, we get significant benefit on these applications. These are the applications where we can harness the large bit level parallelism, millions of bits being operated concurrently at the same time. We get significant energy efficiency benefits compared to CPU, GPU, because we eliminate the data movement, and most of the DRAM chip is really doing processing. These are simulation results. We cannot do this on a real system yet. Okay, in the rest of the talk, I'll just give you some examples. That's probably the most fascinating to us. We basically asked the question. We actually have theorized a lot of this. We simulated things in circuit. We simulated things in system. Can we actually see these functions in DRAM? Ideally, we would like to manufacture DRAM, but that's not an easy task in academia, at least. Even in industry, it's not an easy task. And we wanted to use our infrastructure to check if we can do these operations. This is one of the infrastructures we developed. We called it PyDRAM. And here we violate the timing parameters to perform row clone operations. And we violate the, let me give you the picture of this structure. Essentially, we have an FPGA. Inside the FPGA, we have a wimpy RISC-V processor. This RISC-V processor executes a program. This program, whenever it gets to a page copy, we actually modify the operating system such that the destination page is allocated to the same subarray as the source page. And the memory controller violates the back-to-back activate timing parameter. The RISC-V processor ships the page copy operation to the memory controller. We modify the memory controller to violate the activate timing parameter. And the DRAM chip copies the page to the destination page. And then memory controller returns an acknowledgement saying that I've done the copy inside the DRAM. So we actually built this prototype. We can also do true random number generation. Random function call is also intercepted and sent to the memory controller. And the way we generate random numbers is we violate the activate timing parameter. And some cells fail randomly. every time you violate the activate timing parameter with a specific number. And if you actually profile those cells, they are actually very good random number generator cells, and you keep reading DRAM to get those bits, random bits. So we can actually generate random numbers. And we actually prototype this end-to-end. We open source that if people are interested, they can use it. Unfortunately, this is DDR3 at this point, but DDR4 is also possible to do. And we see significant performance and energy improvements by doing these copying functions. That's by DRAM. More recently, we've shown that you can actually do all of those operations that we've envisioned, functionally complete Boolean operations in real DRAM chips. I'm going to summarize 2 papers in a couple of slides. Essentially, we demonstrated that you can actually copy one row into up to 31 other rows with almost perfect success rate, reliability. You can perform the NOT operation, and you can perform 16 input AND, NAND, OR, and NOR operations, up to 16 input. A very quick example of multi-row copy. That's very similar to row clone that I described. You activate the source row, you activate the destination row, and the copy happens through the sense amplifiers. In multi-row copy, you activate the source row, and then you violate the timing parameters very carefully, such that when you violate the timing parameters, multiple rows get activated, which means that data from source row gets copied into the multiple destination rows. And we've seen up to 31 other rows, at least reasonably reliably. And we call this the multiple row activation. And the reason you can actually activate multiple rows concurrently when you violate some timing parameters is because of the hierarchical design of the DRAM controller. Hierarchical design of the DRAM row decoder. Essentially, you know which rows are going to be activated. And we have actually a lot of results on this one, so we'd be happy to talk. Other people have built prototypes so that you can actually initialize many different rows at the same time and accelerate initialization operations. I'm going to skip the NOT operation. I'm going to give you how we do NAND, NOR, AND, and OR. Basically, by manipulating the bitline voltage, we can express a wide variety of functions using simultaneous multi-row activation neighboring subarrays. Okay, well, that was a mouthful. But if you look at 2 subarrays, I'm showing you 4 cells in 2 subarrays. AB on the top subarray, XY on the bottom subarray. And this is sense amplifier in the middle. This is the open bitline architecture in DRAM. Assume that you had the primitive to do multiple row activation by violating timing parameters, or you baked it into the design of your DRAM. But based on circuit principles, if you activate AB and X and Y at the same time, the sense amplifier would compare the voltage, average voltage of A and B to average voltage of X and Y. Now, if average voltage of A and B is greater than average voltage of X and Y, the top bit line would be 1, the bottom bit line would be 0, otherwise vice versa. So that's what we're going to exploit, basically. We're going to exploit the chart sharing principles of the operation of DRAM. Now, I'm going to term the top subarray as the reference subarray. I'm going to put some voltages over there to AB, VDD, and VDD over 2. And there are ways of actually setting these cells to VDD and VDD over 2 in real DRAM chips. We verified them many times. We open sourced all of these. By setting the top cells, A and B, to VDD and VDD over 2, we can compute a function of X and Y. So if these are set to VDD and VDD over 2, the average voltage is 3 VDD over 4. For the reference, for the compute subarray to evaluate to 1, when all of these rows are activated, the voltages of X and Y should be both 1, logically 1, VDD essentially. And that's a bitwise AND function in the compute subarray. And by nature, you get the bitwise NAND on the reference subarray. So you can compute the bitwise AND and bitwise NAND of X and Y by setting the reference subarray voltage appropriately. Now you can also do bitwise OR and NOR, and that's kind of a nice exam question that I ask freshmen sometimes. Okay, so that's fascinating. And this is theory. We actually tested these in real DRAM chips, violated a lot of timing parameters, and we found out that this is data from essentially all manufacturers. In DRAM chip, you can essentially do the multi-row copy, very reliable. Single row copy is extremely reliable. Multi-row copy is mostly reliable, essentially 99.98%. You can almost use it in real systems if you actually isolate where the errors are, which is something that we actually are doing right now to both understand the fundamental nature of the error mechanisms, as well as potentially understanding, can we actually use this sort of thing in real DRAM chips without modifying the standard, but abusing the DRAM chips. Bitwise AND, NAND, OR, and NOR, of course, are not as reliable for many reasons. And we're actually, again, characterizing the error reasons for it. Some of them are systematic, some of them are random variation. But if you look at this reliability or success rate of these operations are more than 50% in many cases. So essentially, we can do a lot of these operations on real DRAM chips, even if we do nothing to the DRAM chip. Again, I don't recommend this necessarily, but the reason we went this route is to show that even if you do nothing to the DRAM chip, you can actually see these operations that are envisioned by us and others in circuit theory. These are the papers, and there's more to do in this area. I didn't mention a lot of things, but I did mention true random number generation. These were actually the early works that we did to really understand the capability of real DRAM chips. And they did more in this area. I'm not going to bore you with details. You can do physical unclonable functions. You can do lookup table-based execution for more. In flash chips, we actually shown the similar functions. And this, again, we did real studies with FPGA infrastructures with real flash chips to show that you can actually do similar block bitwise, functionally complete block bitwise execution in real Samsung and NAND flash chips. And this is easier in the sense that in flash, you have a controller, and you can modify the controller to maximize the margins, sensing margins, maximize the error correction mechanisms, use the SLT mode, etc., so that you can actually make this completely reliable. And we were able to make this completely reliable by doing so. Of course, at the expense of a little bit increased latency in operations. And you can actually target different applications. These block bitwise operations are actually very good for encryption mechanisms, and we've been examining some of these. I've come to almost at the end. I'd be happy to take any questions at the moment. I'm going to say, maybe before taking questions, I should conclude and I can take more questions. But there's a lot more in this paper, and we've written more papers on the topic. I think the most difficult aspect in this sort of changing the paradigm to be memory-centric is adoption. And I think this is important because adoption is really important. And the good news is I think we're at a different place compared to 14, 15 years ago. A lot of the adoption issues are related to applications, software programming, system security, runtime and compilation infrastructures. But perhaps the most difficult part is really mindset and business models. It's very difficult to change. And these are kind of related, in my opinion. There's business model that is business as usual, processor-centric. Everything, almost every decision we make in businesses and systems are processor-centric. And that affects our mindset, that affects our education and everything. And this is kind of a vicious circle that will keep going, and unless we break it in some way. But I think the good news is people are looking at different ways of breaking it today. So there are many other issues. I will flash these things. Programmability is important. We have some works in this area. We'd be happy to talk about it separately. Coherence is important, I think, especially if you want to partition work. Synchronization is important. Virtual memory is the most difficult part, in my opinion, if you want to be general purpose and support virtual memory. I think virtual memory is very bad in processor-centric systems today. In memory-centric systems, it becomes worse because now you need to deal with virtual memory on the memory side, and we don't have good solutions to this problem. And I think evaluation infrastructures are really important to develop accurately, and we have been developing a lot of these that I mentioned. But I will just mention that we also released recently our RowHammer infrastructure, which is used in both academia and industry. And we'd be happy to take any, we'd be happy to support anyone working on this, and we'd be happy to take any feedback on how to improve this. Okay, I'm going to conclude. So I think we want fundamentally efficient and high-performance systems. But for these, we want computing architectures with minimal data movement. I've given you two examples of designing memory-centric systems. One to solve the technology scaling problems, enabling memory to autonomously manage itself. And the second to solve application and system scaling problems, enabling memory to perform computation. I think there is a lot of work that shows end-to-end results where you can get large energy and performance improvements. And one of the most fascinating results, in my opinion, is unmodified DRAM chips are already capable of computation. I think the good news is DRAM manufacturers have also realized that after we publish some of these results, we have a lot more communication with major manufacturers who wouldn't actually talk about processing using memory for a long time. Now they're thinking, can we actually make it happen? Not going to be easy, but I think it's good to investigate. So I think going forward, memory should be designed as a combined computation and storage substrate as opposed to just a storage substrate. For this, design mindset, flow, and perhaps business models should change. And for this to happen, we need research and design across the computing stack. I will finish with this picture. I think this is a machine. This machine We don't understand enough of it. I certainly don't understand enough of it, but many people in the world don't understand enough of it. What I think is clear is that this machine resembles, its principles of operation resembles nothing like the machines we built in computing. This machine doesn't decouple computation, communication, and storage as much as we decouple them. It's actually much more integrated. Okay, I think I'll stop here. I'm happy to take questions. The rest is really acknowledgement slides. We have a lot of PIM tutorials. We'd be happy to have contributions from folks, and we open source a lot. And most importantly, I'll acknowledge people who have supported this research. There are many folks who have done that. And most importantly, I'll acknowledge my students. Thank you. Happy to take more questions.
Okay, we'll do a couple questions before coffee break, if anybody has. Okay, Onur, thank you very much for the talk. We really appreciate you staying up past normal work hours. But I think we're good.
Thank you.